In this video, we'll learn how to obtain singular value decomposition, SVD, from Python. And we'll show one application of SVD. This is a matrix A. We can represent this matrix A by the three matrices U multiplied by sigma multiplied by V transpose. This is known as SVD. To obtain these three matrices from Python, we just need to call the function SVD from the NumPy linear algebra libraries. So we pass in the matrix A to this function, and this function will return us that three matrix, U, sigma, and the V transpose. This is the printout of the matrix A, the U obtained from the SVD functions, and the V transpose obtained from the SVD function. Now, the S, which is the singular matrix here, which contain the singular values, SVD function from Python return us a 1 by 3 matrices because there are three eigenvalue and hence there are three singular values. But what we really need is a sigma of a size 4 by 3. A is 4 by 3. The sigma must be 4 by 3 as well. We need to convert this 1 by 3 matrix into 4 by 3. This part of the code is to do the conversion of converting the 1 by 3 matrix to a 4 by 3 matrix with the diagonal values contain the singular values. We first create a matrix of 4 by 3, m is 4, n is 3, of zeros. So this line here will create a 4 by 3 matrix of zeros. Then for every row here, we slot in the singular value to the sigma which have the same row and columns. So for example, this position here, we are going to slot in 15.24. This position here, the diagonal position, which has the same row and column, we are going to slot in 3.41. And here, we are going to slot in the third singular value, which is a 0. So after executing this code, we will have a sigma with 4 by 3. The diagonals will have the singular values. Now we can verify that U times sigma times Vt, if we multiply these three matrices together, it will indeed give us the matrix A. So we can verify this using Python. We take the U multiplied by the sigma, then the result of this matrix multiplied by the Vt. And if we print out this value, we get an array of values. And if we check this value with the A here, it's exactly the same. So we have verified that the U, sigma, and the Vt given by this SVD function, if we multiply them together, it does indeed give us the matrix A. In this slide here, we are going to talk about the reduced SVD. This is the SVD we obtained from the Python. Let's call this the full or original SVD. Now, we notice that in this sigma, in this singular matrix here, only these four values are useful. The rest of the values are zeros. We can actually truncate them. If we truncate the values of a matrix, the resultant matrix is known as a reduced SVD. So how are we going to obtain the reduced SVD? For the singular matrix, these are the value we want to retain. Because these two rows are 0, we can actually remove them. And because these two rows are 0, we don't need these two columns here. Now the proving of this, removing these two rows of 0, and we don't need these two columns, the proof of this can be found in the videos from the Brightspace. So now the U is reduced from a 4 by 4 matrix to a 4 by 2 matrix as shown here. This is the reduced U. We can further reduce the sigma by removing the columns here. And because this column is 0, we can actually truncate these rows of the values in V. Removing all this 0 here and remove all these rows of values. So the V now from a 3 by 3 matrix will reduce to 2 by 3 matrix as shown here. And the sigma from a 4 by 3 matrix is reduced to a 2 by 2 matrix. If we multiply the U sigma and the V, the reduced version together, we still will get the A values. There's no loss of information. This is the code in Python to get the reduced SVD. For the U, we are going to retain the first two columns because R is 2. R is 2. So we keep the rows and extract the first two columns. Similarly, for the V, we are going to extract the first two columns as well. Here we are keeping first two rows, but this is a transpose matrix. Keeping the first two rows of a transpose matrix is equivalent to keeping the first two columns of the V matrix without transpose. For sigma when R equal to 2, the sigma will be a R by R matrix. So since R equal to 2, we will have a 2 by 2 matrix. We retain the first two rows and first two columns of the original sigma matrix and save it to a matrix known as sigma R, sigma reduce. So this is the result for U reduce, sigma reduce, and the V reduce. And again, if we multiply these three matrices together, we'll get back the A, the original A matrix. No information is lost because these two rows and these columns, they are all zeros. These are the reduced SVD. Now let's say we want to reduce the matrix further. However, we don't have rows and columns of zeros in the singular matrix. But if we really want to reduce the SVD, the next thing to do is to throw away some useful information. For example, we can remove the 3.41 and retain 15.24. Let's see what is the effect. This row is removed. Because this row is removed, so this column we no longer need it. Similarly, if this column is removed, we don't need this row. So in this case, the R will be 1. This R here will take the value of 1 because we are going to keep the first column only. The U will become a 4 by 1 matrix. The singular matrix will be a 1 by 1. And the V transpose will be a 1 by 3. Now, if we multiply these three matrices together, we'll get a matrix of A. By right, we should get a matrix of A. However, the value of the matrix of A we obtain is a bit different from the original A matrix. But this is not surprising because we are throwing some useful information away in order to further reduce the matrix. However, we can see that this matrix A is not too far away from the original matrix. Let's do a comparison. We have a 4 here, and we have the same 4 here. We have a 1 here, but here we have 1.01. 1 and 1.01 is actually very close. 9.41 close to the original 9. Minus 11 is close to minus 10.58. This is the same. The rest of the value is a bit off, but again, is not too far away from the original values. Now let's summarize. For R equal to 1, the computed A, which is this matrix here, is not too far from the actual A. It's not like here we have a 2, then here we have like a 1000. Bigger singular value is always at the top left-hand corner of the matrix sigma. Now, the biggest singular value is always placed here. The next biggest singular value is placed at this position here, followed by the third biggest values. So the order of the singular values is important. And if you remember, this U1 is correspond to this singular value. This row of V transpose is correspond to these singular values. This position of the singular value contains the most important information about this matrix A. And again, that's why the order of the singular matrix from biggest to the smallest is important. This will facilitate the reduced SVD. If the information in A is lost due to the reduced SVD, this is known as rank R approximation of A. The computer A is just an approximation to the actual A. Now with this, I think it's time for us to see an application for SVD. SVD is used in image compression. Let's understand how a digital image works. This is a digital image. If we divide the image into squares, every square here is known as a pixel. And every pixel has a value known as the intensity value. The value of the pixel will range from 0 to 255, where 255 represents a white pixel, a 0 represents a black pixel. So for example, this pixel here, we can expect the value to be near to 0 because this pixel is black. Whereas this pixel here is white, we can expect the value of this pixel to be near to 255. So basically, this image here is stored in the computer as a set of numbers. And in image processing, we store this pixel value in a matrix. Let's say we want to send out a photo using WhatsApp, and the best quality setting is selected. Assuming the pixel value of the photo is contained in the matrix A. In order for the receiving end to receive the best quality of photo, WhatsApp will send out the photo without any image compression. That is, WhatsApp will send out all the 12 numbers in this matrix A. In another scenario, in order to save the mobile data, user has selected the data saver mode. In this case, WhatsApp will need to apply image compression techniques to minimize the amount of data sent. One image compression technique is the reduced SVD. Instead of sending A, WhatsApp can send out the reduce U, reduce sigma, and the reduce V. That is 4 plus 1 plus 3, total 8 numbers will be sent as compared to 12 numbers here. There is a reduce in the amount of data sent. If we do a simple calculation, that means WhatsApp is sending out only 67% of the original uncompressed data. And that is a saving of 33% of mobile data. Now, when the receiving end receive the reduced U, sigma, and the V, what it will do is they will multiply this matrix together using this formula to restore back the A, which contain the pixel value. As mentioned in the previous slide, this rank R approximation of A is only an approximation of A and not the actual A. Hence, there is a degrade in the image quality in the receiving end. However, most of the time, this degrade in the image quality is acceptable since we are still able to view the image well, and especially when the mobile data is costly. This image here is known as a grayscale image because it does not contain any colors. For color image, every pixel will contain 3 values, the RGB values. The combination in the RGB value will determine the color of each pixel. This is the code for our practical for task 2. This statement here is reading an image using the library in Python. To simplify the algorithm, in order to illustrate the image compression, we are extracting only one channel out of the 3 RGB channels and store the pixel values in the variable img. This is shown in this line of the code. Then we display the image using grayscales. This image here is of size 1006 by 1006. Therefore, it can contain up to 1600 singular values if we use the SVD for image compressions. As usual, we use the SVD function in Python to obtain the U, S, and the VT, and then append zeros to the sigma matrix with diagonal contain all the singular values. In order to compress the image, we need to obtain the reduced SVD of the image. The reduced SVD is obtained using these three lines. Here we are constructing back the image by multiplying the U, sigma, and V together to obtain the rank R approximation of the image. We can see that among the three images here, the lower the value of R, the lower is the quality of the image. That's because we are retaining less information in order to achieve data compression. Do try out practical 4 task 2 on your own.